Assalamualaikum, good day. In this section 6.3, you will be introduced to the transforms of derivatives and you will also learn the steps to execute the Laplace transform method to solve initial value problems. This table of Laplace transform contains an extensive list of formulas of the Laplace transforms of frequently encountered functions and the properties of Laplace transforms. We have already learned the Laplace transforms of the first 8 functions, and today we are going to look at another function given in this table, and that function is listed at row number 19. Okay, so the Laplace transform for the nth derivative of f, which is expressed in terms of t. So its Laplace transform is given by s to the power of n fs minus s to the power of n minus 1 f of 0 minus s to the n minus 2 f prime of 0 minus, and the dot here meaning there are some intermediate terms in between, minus the nth minus 1 derivative of f of 0. Okay, so in other words, we write down the Laplace transform of the function given in the left column is equals to the function given in the right column. Okay, so then in the left column, the function is expressed in terms of t. In the right column, the function is expressed in terms of s. The function at row number 19 in the table of Laplace transform is the nth derivative of f of t. If n equals to 1, it means f prime of t. If n equals to 2, it means f double prime. And if n equals to 3, it means f triple prime. Okay, so in general, the Laplace transform of the nth derivative of f of t is given by s to the power of n fs minus s to the n minus 1 f of 0 minus s to the power of n minus 2 f prime of 0 minus, and some terms in between, minus the nth minus 1 derivative of f of 0. So this is the formula for the Laplace transform of the nth derivative of f. And in the formula, t is said to be equal to 0. And capital letter F is used to denote the function in S. And notice that the degree of S is decreasing from the first term until the last term. And notice that the last term, there's no s involved. And also, the order of derivative of f from the second term until the last term is increasing. Okay, and for the last term, the order of derivative of f is 1 less than the order of derivative of the given function. So if this is of order n, then this one will be of order n minus 1. So let us now use this formula to find the Laplace transform of y prime, y double prime, and y triple prime. So we are going to replace f by the variable y. When we see Laplace transform of y prime, meaning the Laplace transform of y prime as a function of t, y prime of t. So Laplace transform of y prime, n is equals to 1. So just substitute n by 1 into the formula. So s to the power of 1 capital Y s will be the first term, minus for the second term s to the power of 1 minus 1, s power of 0, which is 1, y0, y0. So this will be the last term for the formula of the Laplace transform of y prime, because according to the general formula, the last term is the term where there's no s involved. Okay, here there's no more s, and besides that, the order of derivative of the last term must be 1 less than the order of the given function. So if this is first derivative, then this one, there will be no derivative for the function y. Laplace transform of y double prime, this time n is equals to 2, s squared ys minus, okay, s to the power of 2 minus 1, which is s to the power of 1, s multiplied by y0 minus, and the next one will be s to the power of 2 minus 2, which is 1, s power of 0 is 1, y prime of 0. So this will be the last term for the formula of the Laplace transform of y double prime. In this term, there's no more s involved, and besides that, the order of derivative of this y is 1 less than the order of derivative of the given function. Laplace transform of y triple prime using the same formula, but this time n is equal to 3 is s cubed ys minus s squared y0 minus s y prime of 0. And then there's another last term, which is the last term, minus, okay, notice that the order of differentiation of y increases, so this one must be of y double prime of 0, and the degree of s decreases from the first term until the last term. This is s cubed, s squared, s power of 1, this one will be s power of 0. So the last term has no s involved. So this is the formula for the Laplace transform of y triple prime. Laplace transform is a useful tool for solving initial value problem of differential equations with constant coefficients. So let us now learn the procedure for using the Laplace transform method to solve a given initial value problem. So here are the steps. First step, when they are given the differential equation, take the Laplace transform of each term on each side of the equation, and this step incorporates the initial conditions. By doing so, the differential equation in the unknown function y of t will be converted into a linear algebraic equation in y of s. Okay, let's look at this figure. We are given an initial value problem in terms of y of t and its derivatives. So apply Laplace transform, okay, on each side of the equation, on the left side as well on the right side, and use the given initial conditions in the equation. And once that's done, you notice that the differential equation has been transformed into an algebraic equation in y of s. Okay, so normally it is easier to solve an algebraic equation as compared to solving a differential equation. Alright, so now we're going to solve the transformed equation for y of s. Okay, solve for y of s, and we need to find the inverse Laplace transform of y of s to obtain y of t. Okay, so next step is to get the inverse Laplace transform of the function in s in order for us to get the desired solution y of t. So y of t will be the solution of the initial value problem. Okay, so these are the steps that we have to apply in order for us to solve an initial value problem using the method of Laplace transform. Let us now discuss some problems. Use the Laplace transform to solve the given initial value problems. Question number 1, dy dt minus y equals to 1, y0 equal to 0. Now this is the differential equation of first order followed by an initial condition, and therefore this whole set of problem is known as an initial value problem. Okay, if you observe carefully, this equation is a separable equation, and it is also an equation which is linear in y. So you can solve this equation using the separable method or using the linear method, which you have learned in chapter 2. But now we are more interested to use the Laplace transform method instead. Okay, so how do you apply the Laplace transform method to solve this equation? So firstly, we need to apply the Laplace transform of each term on each side of this equation. The first term is dy dt, which is the same as y prime. So find Laplace transform of y prime minus Laplace transform of the second term, Laplace transform of y, equals to the Laplace transform of the function on the right side of the equation. In this case, the function is just a number 1, so find the Laplace transform of 1. So what is the Laplace transform of y prime? If you do not remember the formula for the Laplace transform of y prime, you need to refer to formula number 19 from the table of Laplace transform. Replace n by the number 1. Okay, so Laplace transform of y prime is s ys minus y0 minus Laplace transform of y. We know that Laplace transform of f is fs, therefore Laplace transform of y has to be ys. Laplace transform of 1, from rule number 1, table of Laplace transform, the answer is simply 1 over s. So this equation has a term y of 0. Now this is actually the initial condition given in the problem. y0 is equals to 0. Okay, so that means this term gone to 0. So what is left is the following: sys minus ys. So these two terms has a common factor ys. So let us factor the ys. So inside this bracket, we write down the coefficient of the ys. Okay, so for the first term, the coefficient is s. And for the second term, the coefficient of ys is negative 1. Okay, so s minus 1 ys is equals to 1 over s. So from this differential equation, we have converted it to an algebraic equation in S. And now let us solve for the ys. Okay, so ys must be equals to 1 over s divided 1 over s times s minus 1. Okay, so this is the function of y of s. Now let us find out the solution for this equation where we need to express y in terms of t. So how to do that? Now we know that Laplace transform of y of t is equals to ys. Therefore, to get y in terms of t, we have to evaluate the inverse of y of s. So in order for us to get y of t, we have to evaluate the inverse of ys. Now ys is given by 1 over s times s minus 1. So the question is, what is the inverse of 1 over s times s minus 1? You know very well that if the function involves a product of linear factors at the denominator, we need to decompose this into a sum of partial fraction. So do partial fraction. 1 over s times s minus 1 is equals to a sum of two partial fractions. The first partial fraction is a over s, and the second partial fraction is b over s minus 1. So use the cover-up method to get the value for the a and the b. Now since a over s, you take s as equal to 0, substitute 0 into the s which is not covered. So 1 over 0 minus 1, that will give a as negative 1. And to get the b is above s minus 1. So assuming s minus 1 is equal to 0, that means s equals to 1. Substitute 1 into the s which is not covered. So b must be equals to 1. So now we got the values for the constants a and b. So substitute a as negative 1. Okay, so negative 1 over s. And substitute b as 1. So b equals to 1. 1 over s minus 1. So this will be the partial fraction decomposition of this function 1 over s times s minus 1. So when we want to get the value, the function y of t, which is the inverse of 1 over s times s minus 1, is the same by writing down the inverse of negative 1 over s plus 1 over s minus 1. Okay, so this function here has been decomposed into a sum of two partial fractions, and now it's easier for us to get the inverse of each of the term given here. Okay, so the answer is y of t equals to, now inverse of negative 1 over s from the table of Laplace transform is just negative 1, and inverse Laplace transform of 1 over s minus 1, use formula number 4 from the table of Laplace transform where a is equals to 1. So the answer for this will be e to the power of t. Okay, so the solution for this initial value problem is given by y of t equals to negative 1 plus e to the power of t. So if you solve this initial value problem using the linear method or the separable method, you should get the same result. Second question, y double prime plus y is equal to square root of 2 sine square root of 2t, y0 is 10, y prime of 0 is 0. Now this is a second order, non-homogeneous linear DE with constant coefficients. Now we can actually solve this non-homogeneous equation by using the method that we have learned in chapter 4. Now this is non-homogeneous, therefore the general solution will be y equals to yc plus yp. And in finding yp, we can either use the superposition approach or the variation of parameters. Now we are more interested to use the Laplace transform method to solve this equation. Okay, so firstly, you find the Laplace transform of the first term, Laplace transform of y double prime, plus the Laplace transform of the second term, Laplace transform of y, is equals to the Laplace transform of the function on the right side of the equation. Okay, now Laplace transform of the square root of 2 is a constant multiplied by the sine function, so we can factor the square root of 2. So we get square root of 2, Laplace transform of sine square root of 2t. After this, we need to write down the formula for the Laplace transform of y double prime. Okay, recall formula number 19 and in the table of Laplace transform where n is replaced by the number 2. So the formula says Laplace transform of y double prime is s squared ys minus sy0 minus y prime of 0. So this is the Laplace transform of y double prime. Plus Laplace transform of y is ys Okay, we know transform of f is fs, therefore transform of y must be ys, is equal to square root of 2. Now Laplace transform of sine square root of 2t refer to formula number 5 in the table of Laplace transform, where k is equal to square root of 2. So it will be k over s squared plus k squared. K is square root of 2, so square root of 2 divided by s squared plus 2. Now we are given that the first initial condition y0 is 10. So after this we need to replace y0 by the number 10, and y prime of 0 is equal to 0. So need to replace this by 0. So here's what we are getting. S squared ys minus, now s times 10 can be written as minus 10s, and this is already 0, plus ys. Now square root of 2 multiplied by square root of 2 gives the number 2. So on the right side we have the function 2 over s squared plus 2. The next step is to shift the term without the ys on the right side. So this term has no ys, so you need to shift this to the right side. So on the right side we get 2 over s squared plus 2 plus 10s. On the left side we have to factor the common function y of s. Okay, so these two terms have the common function ys, so factor the ys, and inside here we write down the coefficient of the ys. So the first term, the coefficient of ys is s squared. For the second term, the coefficient of ys is plus 1. So we write down plus 1 here. Okay, so this differential equation has now been transformed into an algebraic equation in S. So next step is to solve for the ys. Right, so we need to get an expression for the ys. How to do that? We have to divide everything by the coefficient of ys, which is s squared plus 1. When we say we solve for ys, we want the coefficient of ys to be 1. Right, so to do that, divide everything by s squared plus 1. So for the first term, when we divide it by s squared plus 1, we get 2 over s squared plus 2 multiplied by s squared plus 1. And for the second term, we get 10s divided by s squared plus 1. Okay, so this is the function s. Our aim is to find the solution y in terms of t, not y of s. So we need to find y in terms of t. So to get y in terms of t, we need to get the inverse of the ys. Okay, so we need to get the inverse of all of this. So how to determine the inverse of this function? We already learned this in chapter 6.2. Okay, finding the inverse functions of finding the inverse of functions. So firstly, we can use the linearity of the inverse Laplace transform. You can split this into two problems of inverse transforms. So you get the inverse of the first term plus the inverse of the second term. Now for the second term, I have factored the number 10, okay, leaving s inside. 10 times s gives back 10s. Okay, for the first term, notice that it involves at the denominator a product of two quadratic factors. So in this case, we have to apply partial fraction to decompose this into a sum of partial fraction. So 2 over s squared plus 2 times s squared plus 1. Okay, split this into sum of two partial fractions. So the first one, the denominator contains the first factor, which is s squared plus 2, and the second one contains the second factor, s squared plus 1. Right? And since for the first partial fraction, the denominator is of degree 2, and therefore the numerator must be of degree 1. So we write down a linear factor as plus b. Similarly, for the second term, the denominator is of degree 2, therefore the numerator must be of degree 1, a linear factor in the form of cs plus d. So there are four unknowns, a, b, c, d, which we need to find out the values for those unknowns. Okay, equals to, right, get the common denominator of these two functions, and then we can cross multiply as plus b multiplied by s squared plus 1 plus cs plus d multiplied by s squared plus 2 divided by the product of these two. Now this is an equality. That means the function on the left side must be equal to the function on the right. So in other words, the numerator on the left must be the same as numerator on the right. So now I'm going to expand the numerator on the right side. We get a as cubed plus as plus bs squared plus b plus cs cubed plus 2cs plus ds squared plus 2d is equal to 2. Alright, now we're going to group the terms with the same powers of s. So as cubed plus cs cubed factor s cubed, we get a plus c times s cubed. Bs squared plus ds squared factor s squared. Inside here we write b plus d and as plus 2cs. Okay, factor the s, so inside is a plus 2c, and then we collect the constant terms b plus 2d. Okay, this one has no s at all, is equal to 2. So we have to form equations to get the unknowns a, b, c, d. So the first equation that we can get is the coefficient of s cubed. A plus c is the coefficient of s cubed, but on the right side there is no s cubed. That means the coefficient of s cubed on the right side is 0. So this will be the first equation. Then coefficient of s squared, compare left side with the right side. B plus d on the left side is the coefficient for s squared. There's no s squared on the right. That means b plus d must be 0. This 0 is the coefficient of the s squared on the right side. And then coefficient of s on the left is a plus 2c. And on the right side there's no s. That means the coefficient of s on the right side is equal to 0. And the term without the s is b plus 2d, and on the right side the term is 2. So b plus 2d is equals to 2. So we have 4 equations with 4 unknowns. I think it's easy for us to solve 1 and 3. So if you solve 1 and 3, we'll get c and a both equals to 0. And when you solve equations 2 and 4, we'll get d as equals to 2 and b as equals to negative 2. Okay, so next step is to substitute a by 0 and b by negative 2, c by 0 and d by 2. Okay, so this is what we are getting. Inverse of, okay, this is the function. Now we have already decomposed it into a sum of two partial fractions. So a is 0, so 0s, and b is negative 2, divided by s squared plus 2 plus, now c is also 0, so 0s, plus d is 2, divided by s squared plus 1, plus the second term. Alright, now if you look at this part here, we can actually apply term-wise division. The first term divided by denominator minus second term divided by denominator, plus, okay, this term here divided by this denominator plus this term here divided by the same denominator. Right, so y of t is equals to, now 0 divided by anything is 0, minus 2 times s squared plus 2. Now negative 2 is a constant, you can factor the negative 2, leave 1 inside, so negative 2 inverse of 1 over s squared plus 2, plus, and for this term here, this is already 0, so plus 2 divided by s squared plus 1. Okay, so 2, leave 1 inside, so 2 times 1 gives back 2 divided by s squared plus 1. So 2 times the inverse of 1 over s squared plus 1 plus the last term. So there are 3 inverse problems that need to be computed. Okay, so we get, for the first inverse, we have already learned how to evaluate this kind of problem. Okay, this one here matches the formula number 5 in the table of Laplace transform, inverse of k over s squared plus k squared. So if k squared is equal to 2, then the number appear up here must be square root of 2. So you write down square root of 2 and divide back by square root of 2 to get back the same function. Okay, square root of 2 divided by square root of 2 gives back the number 1. Alright, so this is the function that we have. This is the function that we have manipulated, and we are getting this one. And now we are going to write down the final answer, negative 2 over root 2, and the inverse of this function is given by sine square root of 2t based on formula number 5, plus 2 times, this one also we can just apply formula number 5 where k is equals to 1, so 2 sine t, and for the last part we can apply formula number 6 where k is equals to 1, so 10 cos t. Right, so this is the solution for the given initial value problem. If you use the method of superposition approach or the method of variation of parameters to solve this non-homogeneous equation, you should get the same result. So that's all. The end. Thank you.